treatment and medicines are given in the right doses. Small error can be dangerous. In manufacturing and trade, metrology ensures products meet standards and customers get what they pay for. Metrology protects consumers from cheating, poor quality, and unsafe goods. Metrology may be invisible, but its impact is everywhere. Accurate measurements build the trust, safety, and fairness. Metrology matters.
In every second, a silent language is spoken across East Africa. It's not Swahili, it's not Luganda, or it's not English. It's a language of precision, metrology. In health, metrology is the boundary between cure and crisis. When a doctor prescribes 5 meals, it must be 5 meals. Accurate measurements save lives and ensure our hospitals are safe. In manufacturing, it's about the perfect fit. Without standards, our industries can't compete, from the smartest bolt to the largest engine. Metrology build a made in East Africa quality. And in trade, it's about your pocket. Metrology is the referee that ensures 1 kilogram in Nairobi is the same as 1 kilogram in Dar es Salaam. As a student, we are the future of this community. Demystify metrology isn't just for scientists, it's for every consumer who deserves protection and every business that wants to grow.
Mainstreaming metrology, enhancing protection, powering East Africa. My name is Elias Robert Benbai, and I believe in the standard of precision. So let's make every measure count.
In every second, a silent language is spoken across East Africa. It's not Swahili, it's not Luganda, or it's not English. It's a language of precision, metrology. In health, metrology is the boundary between cure and crisis. When a doctor prescribes 5 meals, it must be 5 meals. Accurate measurements save lives and ensure our hospitals are safe. In manufacturing, it's about the perfect fit. Without standards, our industries can't compete, from the smartest bolt to the largest engine. Metrology build a made in East Africa quality. And in trade, it's about your pocket. Metrology is the referee that ensures 1 kilogram in Nairobi is the same as 1 kilogram in Dar es Salaam. As a student, we are the future of this community. Demystify metrology isn't just for scientists, it's for every consumer who deserves protection and every business that wants to grow.
Mainstreaming metrology, enhancing protection, powering East Africa. My name is Elias Robert Benbai, and I believe in the standard of precision. So let's make every measure count.
In every second, a silent language is spoken across East Africa. It's not Swahili, it's not Luganda, or it's not English. It's a language of precision, metrology. In health, metrology is the boundary between cure and crisis. When a doctor prescribes 5 meals, it must be 5 meals. Accurate measurements save lives and ensure our hospitals are safe. In manufacturing, it's about the perfect fit. Without standards, our industries can't compete, from the smartest bolt to the largest engine. Metrology build a made in East Africa quality. And in trade, it's about your pocket. Metrology is the referee that ensures 1 kilogram in Nairobi is the same as 1 kilogram in Dar es Salaam. As a student, we are the future of this community. Demystify metrology isn't just for scientists, it's for every consumer who deserves protection and every business that wants to grow.
Mainstreaming metrology, enhancing protection, powering East Africa. My name is Elias Robert Benbai, and I believe in the standard of precision. So let's make every measure count.
In every second, a silent language is spoken across East Africa. It's not Swahili, it's not Luganda, it's not English. It's a language of precision, metrology. In health, metrology is the...
In most parts of life, being close enough is fine, but in a hospital, close enough can be very dangerous. This is where metrology becomes a matter of life and death. Think about a baby in an incubator. The temperature must be exact. Now think about a patient on a heart monitor or a child receiving a dose of medicine. If the equipment isn't calibrated, the diagnosis is wrong and the treatment fails. Metrology in health ensures that every medical device, from a simple thermometer to a complex MRI scanner,
tena. For the next part, I'd want to welcome our next presenter. Wahoo. We are welcoming our next presenter. So our next presentation will be from Dr. Joshua Njiru, will be giving us an address on the role of research development and innovation in the elevation of national metrology institutes. Karibu daktari.
Good afternoon, ladies and gentlemen. Good afternoon. So my name is Dr. Njiru. All protocols observed. I am in great pleasure to stand here in front of you today to give a talk and to share some insights on where the African National Metrology Institute see ourselves with respect to research, development, and innovation. For the, sorry, oh yeah, is it okay? I need to make it bigger, thank you. Yeah, thank you. All right. Yes. I'll be sharing with us a talk on empowering Africa's National Metrology Institutes, catalyzing research, development, and innovation. We look at the global, continental, and regional perspective with respect to research, development, and innovation. And as I mentioned earlier, my name is Dr. Joshua Njiru. I'm the Chief Manager, Research and Development, Kenya Bureau of Standards. Earlier on today, a number of speakers took this podium and spoke about research, development, partnerships, collaborations. And I will delve a little bit on what are the opportunities that are there in the African continent, in the region, and also give an exemplar of what has been done by Kenya Bureau of Standards through our National Metrology Institute to catalyze and develop and create an environment that is robust for research, development, and innovation activities. Just recently, the World Intellectual Property Organization tabled the Global Innovation Index for 139 countries. And this is a ranking as per the Global Innovation Index for East Africa as ranked by WIPO. So Kenya being the first in the region at 102 out of 139 countries, followed by Rwanda at 104, 121, all the way, I only took the top 5. Top 5, and you can see that our top 5 is 134 That is the scenario from the Global Innovation Index. Why is this important? A high ranking in the Global Innovation Index attracts foreign investment and technology transfer, boosts competitiveness and inter-Africa trade, and signals readiness for innovation-driven growth as envisaged in the African Agenda 2063. The reason why I start with this is for us to see our current position as a region, as a country, the different countries that are represented here, and ask ourselves what is missing or what is there to be able to increase our ranking in the Global Innovation Index. With respect to national metrology institutes, we are an enabling environment, and what can be done to be able to go up in the innovation index. Under the African Union Agenda 2063, clear aspirations have been stipulated for science, technology, and innovation. With the agenda of the African Agenda 2063, the Africa we want: prosperous, integrated, innovation-driven continent. So where is the place of research, development, and innovation in the African Union Agenda 2063? It has been well defined, with STI and R&DI priorities highlighted as science, technology, and innovation skills revolution by building world-class research centers and STEM talent, sustainable and inclusive economies, standards for renewable energy, climate resilience, and green technologies, wealth creation and industrialization, the value addition through precise measurements and quality infrastructure, health and food security, accurate metrology for medical devices, vaccines, and agricultural inputs. So metrology role is fundamental, is a foundational enabler for quality, trade, fairness, and technological sovereignty, where in political outlook is the information that is required and also the participants of the technologies that are being developed to be participating in it. So what is our role as researchers, as national metrology institutes? A couple of speakers stood here and spoke about research development, research in the institutions. So where we can see that we have got a supporting framework from the continental front. And coming closer home to the strategies, in 2014, when the African Union Agenda 2063 was declared, the first 10 years of the African Agenda Union was to develop a science, technology, and innovation science strategy from 2014 to 2024. And it had 4 pillars: research infrastructure upgrade, skill and competence, entrepreneurship and innovation, and an enabling policy environment. The research, development, and innovation platform was strongly supported through the African Agenda Union. And now after 2024, when it came to its maturity and they took stock, there is now the new science, technology, and innovation strategy for Africa that started in January of 2025 last year, and that will mature in 2034. I'll give a lot of background, and then I'll go to the reason why I am giving this background with reference to the National Metrology Institutes. The new one, the strategy for science, technology, and innovation, where research and development is highly emphasized, is more ambitious, is action-oriented, with 5 sectoral priorities in agriculture, health, ICT, energy, and environment. How do we, as the National Metrology Institutes, find our place in this strategy? This is just to show what were the lessons that were taken from the Science, Technology, and Innovation Strategy for Africa that matured in 2024, and the remedies that have been done. In the current strategy of the African Union, Agenda 2063, highlights the different sectors that I have previously mentioned, but the outcome is to accelerate African transition to a knowledge-based and innovation-led socio-economic development. So there is a lot of emphasis and support on research, development, and innovation. How is this cascaded down, and where do we find our position as the National Metrology Institutes? You can see there how it is cascaded down, and you can be able to identify yourself as an academic / national research institute, regional and international, private sector, civil, member states through the ministries. We have a platform that has been created for us. Coming closer home to the East African Community Vision 2050, science, technology, and innovation, a few enabling platforms have been established through capacity building and STI infrastructure, research, innovation, and entrepreneurship, research mobilization and partnerships, and an enabling environment. We have desks, an STI observatory that has been established at the East Africa Community Region. East Africa Community AI Alliance launched in 2025, and also the integration into the 7 East Africa Community Development Strategy. Strengthened university and industrial linkages. We are yet probably to fill this. And metrology is critical for harmonized standards, trade facilitation, and industrial competitiveness. Now, the key priorities that we can be able to take home from the 2 policies and platforms that have been created through the Agenda 2063, African Agenda 2063, and the European and the East Africa Community Agenda for 2050, that we need to build a robust infrastructure and capacity. African National Metrology Institutes, where we are part of it as the East Africa metrology players, must urgently modernize laboratories to support advanced measurements. For example, in nanotechnology, renewable energy, and biotechnology. This directly supports the African Union Science, Technology, and Innovation Strategy for Africa 2024, and now the one for 2034, and the East Africa Vision 2050, targeting on universal energy access and infrastructure connectivity. Fostering collaborative research and partnerships. The National Metrology Institutes that are here, and you are interested and you have mentioned on issues to do with research, then we must foster formidable, strong collaborations and partnerships. And then integrating metrology into emerging technologies. This is essential for the Agenda 2063, climate resilience, economies, and also the East Africa Community Vision 2050's clean energy goals. Policy alignment and sustainable funding. As the African National Metrology Institutes, right from the region, we must advocate for increased national budgets and public-private partnerships. Learning from successful models in developed worlds to close the technology gap and accelerate economic growth. Just to show an example of the comparative analysis between Africa and other developed nations when it comes to financing and the capabilities in research, development, and innovation in metrology. So we have one NIST. Their budget allocation per year is close to about $1.4 billion in research, only research. And you look at the areas of research, CHIPS Act metrology program. This is for the conductors and the semiconductors that is it's actually been supported by an act of parliament. Quantum information science and AI standards, advanced manufacturing and semiconductor metrology. This is funded. This is a National Metrology Institute funding research. Then we go to China, 620 million. National key research and development metrology programs that are being funded. Quantum technology and green energy metrology. Digital transformation and AI standards. You go to Germany, PTB, 385 million with collaboration with EAMET and member states. In UK, funding 175 million, digital and AI standards program. Climate and net zero, these are projects that have been funded and they are not in a university. They are not in an institution of higher learning. These are projects that are funded and they are being conducted by scientists and personnel from the National Metrology Institutes, in the like of you and I who are here in this room today. Then we have South Korea at 168. Now, with the technology advancement, I was able to pull out down something, and you can see the dominant themes that they're focusing on: quantum technologies, AI, digital standards, semiconductors, green energy, and advanced manufacturing. So with a lot of information available online now, I pulled a contrast of what we have in Africa. Top 5. So number 1, South Africa, combined is more than all the other countries, including our very own that are here. We have Kenya and Rwanda. This is the kind of data and the allocation and the seriousness as a region that we are giving to research, development, and innovation. These figures, I got them from all the way from 2024, 2025, and from different platforms. And most of the African NMIs heavily rely on external funding. Actually, the figures that are projected here are purely from captured by the development partners. So this is a scenario now that we have to grapple with as the National Metrology Institutes. When you compare with what is happening globally with also what you've been able to do, we have a far way long to go. We have a lot of catching up to do. I want to show you an exemplar of what we have been able to do as Kenya Bureau of Standards to try and turn around this narrative, that we are able to demonstrate and show that the National Metrology Institutes can competitively bid for the space in research, and also they can also be able to tap into the research, development, and innovation platforms that are there globally. So it all started with, of course, our Vision 2030 and the strategic plan for Kenya Bureau of Standards 2023-2027, which clearly outlined and declared itself on the importance of research, development, and innovation, and why, as an institution, we needed to prioritize research, development, and innovation. And as such, supported by the strategic plan, we were able to develop our very first research, development, and innovation policy of 2023. We had many mistakes to make and many lessons to take. We brought in strategic partners and key stakeholders. We sat together with the regulators, the National Commission for Science, Technology, and Innovation, who regulates all the research that is done in Kenya. We sat down with the Kenya National Innovation Agency, who will actually commercialize the research outputs. And also we sat down with the National Research Fund. The National Research Fund is responsible for funding and giving grants to institutions, research institutions, and researchers. And then after 2023, we also went on and we have now reviewed, after 3 years, our research, development, and innovation policy. We have the strategy, and also we have a roadmap on how to deliver that. So what did we realize after that shortly? Just to mention on what is basically for an exemplar that we share from Kenya Bureau of Standards is the purpose of the research and development activities or initiatives within Kenya Bureau of Standards is to provide clear direction and robust solution to strengthen research, development, and innovation at KEBS. I don't have to read this, but just to mention on highlight that every research, development, and innovation activity within Kenya Bureau of Standards is meant to support standardization, metrology, and conformity assessment. So if you read, for example, our priority area number 2, RDI initiatives will focus on creating and updating standards for new and innovative products, formulating novel test methods, publish calibration and measurement capabilities, develop supervision schemes, advancing industry collaborations, transforming internal process through innovation. We have those as priorities. So the National Metrology Institute is also taken care of in this category. But very important from our policy is a commitment that is made to support the National Metrology, to support the research, development, innovation initiatives. The chair of the council was here this morning, and one of the things that the NAMIT itself is in the allocation of 2% of KEBS budget to research, development, and innovation activities. So after all this, a lot of work that has been done by very committed people, established a committee that is very, very important. This is not a departmental or a one-man thing. The KEBS Research and Ethics Review Committee is a committee that reviews concepts, that reviews proposals from all the departments within Kenya Bureau of Standards, look for their suitability and alignment to the goals and aspirations of the institution, and recommend them for funding. So this is one of the ways that we have been able to support and that we have been able to actually not only operationalize, but also get to a point whereby now, after all that, we have been, we have the registration of Kenya Bureau of Standards from last year, September, as a research institute by the National Commission for Science, Technology and Innovation, having fulfilled the requirements of Science, Technology and Innovation Act of 2013. So this now allowed us as an institution to actively ask and bid for grants. And this was quite pivotal, because now it becomes at times when you're requested to, you're asked, is your facility, we see your mandate is not in research. But I don't know about the jurisdictions where different people come from. In our law in Kenya, there's a provision whereby if you're active in research, if you have a department, or if you're a section that you can be able to beef up and build up, that is regulated and monitored by the National Commission for Science, Technology and Innovation, you go through quite a rigorous process. And once you've fulfilled all the requirements, you are actually certified as a research institute. Now, this committee here, the KEBS Research and Ethics Review Committee, ideally is what you'd have those people coming from academia and coming from research institute, especially that deal with human subjects, animal. They call the Ethics Review Committee. The KEBS Research and Ethics Review Committee is the ISAC, Institutional Scientific Review and Ethics Committee. But for KEBS, we have been able to domesticate it to our functions on how we want it to support research and development initiatives in an NMI. And this is undergoing accreditation by the National Commission for Science, Technology and Innovation. We have already been done the first round of assessment. So after this, the test environment as a national metrology institute or national standards body was actually to call for interests in research, development and innovation initiatives and drives. And this was our first call that was done on 3rd, I think it should be 3rd of February, and closed last week on Friday. And this is our first call. And what we have here is over 50 concepts from researchers, scientists within KEBS who have concepts, who have researchable questions that will improve and support the mandate of Kenya Bureau of Standards. And it is all spread. Yeah, metrology and testing, they took the lead at close to about 18 concepts that were submitted. And even the MD's office, our own MD is interested in research. They have submitted, the MD's office have submitted a concept for review, for funding. We have human resource and administration, finance strategy, metrology and testing, standards development and trade came in 3rd, quality assurance and inspection, internal audits, and the MD's office. So this is after now we have done the process. As I said, this is just an exemplar to show what the National Metrology Institute we have done, what platforms we have leveraged on, and the opportunities that are there. Is now we are actively involved in research and also going out seeking for funding from development partners. But again, as I mentioned, it is a commitment of the institution, the commitment of the national standards body, from the approved strategic plan and the research development and innovation strategy, that also commits to allocate at least 2% of its budget to research development and innovation activities. Thank you so much. Metrology is no longer the Africa silent enabler for the Africa we want. And together, let us empower Africa's national metrology institutes to become the powerful engines of research, development, and innovation that will measure, drive, and shape the prosperous, integrated Africa we want under Agenda 2063. Thank you, ladies and gentlemen.
Thank you, Dr. Njiru, for that insightful presentation. We have noted a few milestones like registration by NACOST and allocation of $2.1 million for research. And congratulations to you and your team. Let's please clap for him once more. Santeni sana. Now for the second part of our afternoon presentation, I'd like to welcome delegates from South Sudan who will be the chair of this session. I would like to welcome on stage Mr. Emmanuel Atari from South Sudan Bureau of Standards. It tells me Atari doesn't mean danger, but means someone was born at night. And since I was also born at night, it seems this is the podium for the people born at night. Karibu Bwana Atari. Clap for him, please. Asante.
Good afternoon. Asante sana Bwana Engineer Kovur. So I believe by the end of this conference, I will go home with a lot of vocabularies from Swahili. And then I will come back as your shemeji. So I hope so. Okay, for the purpose of saving time, as we are going to have our second session, may I ask my brother from another mother to give us some warm-up exercise? Joseph Kadenge. Please let's have some warm-up exercise so that the digestion speed up. Thank you so much, my brother Kadenge. Okay. Thank you so much, Kadenge. Now, I think we have started our first session in the morning. It was about metrology practice, of which Kadenge has just demonstrated to us that we need to practice metrology. To give you a short story, I remember when we first landed here, and then we were together with one of my Tanzanian friends. So when we board an Uber, so we went to another apartment, and then because of our budget, we started doing some calculation, of which we said, okay, the distance from the venue and where we live, how much will it cost? Of which my colleague Boniface said, okay, it's time for us to start practicing metrology. Thank you so much, Boniface. Okay, the next presenter is going to present on calibration in vacuum pressure frontier, high precision calibration of Teledny Hastings thermophile vacuum reference sensors in RASCA 2465A systems using capacitative diaphragm standards. It's going to be none other than Sylvester Memia. So the podium is yours, but for the purpose of time, please be precise. I would suggest you take 15 minutes.
Soma hiyo label 20023 tumakoda kikisha guarantee usipate umepima maji usipate umekupima maji single standard ya quality usipate cheki kama hustler you wanna go faster 1545 si tuta come through si stress my guy. Soma hiyo label 20023 come through if you know what that means. She can number 20023 slide through if you know what that means.
Okay, good afternoon. My presentation will actually be touching on what Dr. Njiru had already talked about, that is nanotechnology. And nanotechnology, as we know it, came from, there's a lecture that a famous physicist gave by the name Richard Feynman, that there is more room at the bottom. That was in 1959. And that actual talk is what triggered the nanotechnology revolution that we currently experience. And some of the nanotechnology, we hear of such big words, but we can't really relate. But I can assure you, we keep on using those technologies. That is your phone, and you can be able to put it on the rotation to get a horizontal rotation. The smartphone, the smartwatches that you use, that is still nanotechnology, able to measure your pulses, the steps that you've taken. All those are nanotechnologies, more specifically accelerometers. But today what I'm going to talk about is on the metrology bit, and that is mainly on pressure. Okay, so my name is Sylvester. I'm a mechatronic engineer. This is my work experience. And also those are my registration for the memberships that I partake in. So as I've been introduced, the area of focus will be in vacuum pressure measurements. And it's more critical, particularly for the metrology that we are doing, because vacuum measurements are the reason as to why we have clean products, like for the clean rooms which are used in pharmaceutical industries. So you need accurate ways of measuring the vacuum. So it's something that is critical for metrology. So one of the ways that vacuum is used, particularly for us in the laboratory, is in the piston gauge, which are the primary units for pressure into the realization of Pascal. So the method that we usually use one in doing the absolute measurements that we partake in, those is as given by this particular formula. So for the first bit of the formula, basically it's the normal formula for pressure equals to force over area, with the A being the effective area and then the P being the residual pressure. So that residual pressure is the one that I'm going to be looking at this afternoon, and I really want you to take note of that, because the residual pressure is important when you're doing something called absolute pressure metrology. Okay, so there are two methods of doing absolute pressure measurements. That is by adding atmospheric pressure to this particular P gauge here. The gauge being the gauge pressure. So how do you obtain the gauge pressure? You remember the formula that I had shown, this here, this bit, the force over effective area. The force is being provided by masses, and the area is being provided by also doing accurate measurements of dimensions. So this particular way of doing the absolute pressure measurement, and there was also the vacuum reference method. So for the vacuum reference method, you mainly rely on these residuals that I had talked about earlier. So this method mainly is used for, you'll find it in the type of primary units that are usually located in NMIs, like the RASCA 2465. So whereby we have the residual pressure being measured by the thermopile sensor that is, we are going to show how it's going to be calibrated. So RASCA is a company from America that and currently was just absorbed by a Fluke. They provide this particular standard, primary standard, whereby they realize pressure by method of generating pressure by masses being laid on top of a particular piston that has a specified dimension. And that dimension has to be quantified also with the uncertainty associated with it. Okay, so now let me come to the thermopile vacuum reference sensor. The thermopile vacuum reference sensor is the one that is going to give us the residual pressure that are shown in the formula. So the thermopile vacuum sensor, basically it's called thermo because the mode by which it measures pressure is through temperature gradient. So there's this thing called the Seebeck effect, whereby you can see the voltage being related to a temperature difference and the alpha being the Seebeck coefficient. So basically, if you get two dissimilar metals that are in different temperature gradients, you're going to have a flow of charges due to the charge carrier diffusion. Charge carrier diffusion being triggered mainly by the kinetic energy of the atom of the electrons, and also by the fact that you have now the electrons flowing from the region of high concentration to a region of low concentration. So basically, the alpha there is able to quantify how that charge carrier diffusion is happening. So from that, we get the sensor giving us the output voltage, which is now dependent on pressure. So how does pressure relate to temperature? Now, for the thermopile sensors, basically what they do is you have the charge carriers flowing from a region of high temperature junction to a region of cold temperature junction. How do you get them to flow? You have to create a gradient through which is going to trigger that flow. And the way to trigger that gradient is by playing around with the temperature differences. So for thermopile vacuum sensors, basically what they do is you have a gas now coming into play, whereby the gas is able now to be the one that's triggering the temperature gradient. So the gas, which has to have some particular thermal conductance, is able now to be able, dependent on the pressure that is the gas has, it's able to vary the particular voltage that you're able to measure the flow of current. So you have gas that is able to take away the heat from the hot junction. As I had told you, you have two junctions, the hot junction and the cold junction. So if the gas is able to take away heat from the hot junction towards the to the cold junction, which basically is a heat sink, you are going to create a thermal gradient, and that thermal gradient is what is going to trigger that charge carrier diffusion. So in there are two architectures that are usually involved with these particular thermopile sensors that are able to measure temperature. So measure pressure, sorry. So there is the cantilever beam sensor, and for engineers, I know you, particularly if you are a mechanic or a civil engineer, you'll know about cantilever beams. So in a cantilever architecture, you have this particular bit of an extended arm or link. So that extended link is whereby you find the hot junction being located. So how do you create a hot junction basically? And mind you, when you look at this diagram, understand these are very small component that is in the region of around 10 millimeters in size for the sensor, because it's basically a sensor. But the way the architecture is, you're looking at things that are within the region of micro. It's a micro device, okay? So you have the cantilever beam. The cantilever beam is the one that is housing the temperature, the hot junction that is in this sensor. So how do they attain the hot junction? Mainly, you have the resistance. See, they create small resistance that are in the micro level, and when electrons are flowing, of course, they are going to experience some resistance. So that resistance is what is now converted to the heat energy. And that heat energy now, when it is concentrated on this particular region of the cantilever beam, or basically the tip of that cantilever beam, it has to find a way of flowing. So on that flow is where you have this gap, and that gap is what actually is housing the gas that you are trying to determine the pressure of it. So what happens is, if this gas is in the molecular density, or basically there is more pressure or more molecules of that gas in this region, you're going to have some conduction of heat. If the gas is low in density, or basically low molecular density, meaning low pressure, it means you're going to have a higher concentration of heat on this particular tip. So basically, by playing around with pressure, which just basically translates to the molecule density of the gas in this region, you can be able to basically determine accurately where the pressure is. So for high pressure, this particular method is not so good, but for very high pressures, and when I'm talking of high pressures, we are looking at things around above 130 Pascal. Going beyond that, you're not going to have what we call a linear or a proportional response to the way the sensor is going to respond. So what pressures we are actually targeting are pressures below 130 to around 0.3 Pascal. Okay, So in case the pressure falls, basically playing around with the number of molecules in that region, what you are going to have is the heat is not going to be conducted proportionally, which is the issue of the thermal conductance of that gas. So what happens is that the temperature gradient is going to be high, and that can be actually converted now to the signal that you can, using signal conditioning circuits, you can be able now to translate that to pressure. So based on the heat conduction, okay? So there is that particular architecture, and then we have the floating membrane architecture. The floating membrane architecture is different from the cantilever beam. Instead of having that link being suspended in air, you have an entire plate now being suspended by several arms. This particular method, it's a bit better because it usually uses a feedback loop to monitor the temperature gradient flow, and it operates under that constant temperature measurement mode. So what do we look at the feedback? The feedback loop basically looks at how much temperature is being conducted away by the gas, and then it's able to readjust the amount of current that is flowing through that particular circuit. And the suspending arms are the ones that basically carry those particular the particular flow of the flow circuits that are able to heat up that particular plate. I want you to look at that floating membrane as a plate. It's basically just a plate with some resistance attached to it. So what are the differences between the two architectures? You'll find that for floating membrane architecture, it is directly proportional to the heat conducted by the gas. The voltage generated, or basically the signal output you get, is directly proportional to the heat conductance of the gas. But while the cantilever beam, the relation is not directly proportional, as you can see from the research. It's basically an issue of the proportionality will not be directly correlated to the way the signal is produced due to the heat conductance. So you can basically look at that. Okay, now need to provide traceability for thermopile. The reason as to why we came up with this research was to basically provide show a way of calibrating that thermopile reference sensor. So thermopile reference sensors exhibit the following responses. They are nonlinear in high flow regimes. Basically what I was telling you, for high flow regimes you have basically high pressure, and under such circumstances the sensor is not going to be able to actually translate that signal directly to the heat conduction. They are temperature sensitive, meaning if you are doing your pressure measurements, since they rely actually on temperature gradient, you have to take consideration of the ambient temperature under which you are doing the calibration. Of course, all sensors, due to drift, they are going to, you have to check the drift, because over time the sensors wear out, the characteristics of the material change, so you are going to have the drift. And they're also gas type dependence, meaning the way they conduct heat or the way they do their measurement will be dependent on the type of gas you have in that particular chamber, whereby if you have things like monoatomic gases, when you're looking at maybe oxygen, and the diatomic gases like N2, you are going to have a different measurement as compared to each of the. Therefore, traceable calibration against high accuracy reference standard is required. So you have to actually establish the traceability, because you are trying to find to get absolute pressure measurements that are as highly as accurate as possible. Okay, so now, how do you establish that traceability? The only other way to establish that traceability is through using this other sensor called the capacitive diaphragm gauge, which is going now to act as the reference sensor. So for the capacitive diaphragm gauges, they measure pressure by means of playing around with the capacitance of two plates, or the distance between two plates, and the permittivity of a capacitor. For engineers, you'll know that for any particular capacitor, this is the operating formula, this E, which is the permittivity. You have the diaphragm area and the distance between the plate electrodes. So if you play with the distance, adjusting the distance of that particular capacitor, you can be able to accurately measure the pressure. So what happens is, you have a thermopile connected on one end of the a setup that you can do the calibration. So like this one. So whereby you have the capacity, the reference standard here, or the transfer standard for metrologists, and then you have this particular thermal reference sensor. So what happens when you subject both of them to the same pressure? This one will be using temperature gradient to monitor the vacuum pressure, while this one will be playing with that distance, whereby if you pressurize it, the plates come closer to each other. If you depressurize it, they move away from each other. So it's playing about with that particular D of the capacitance. So one of the advantages of using the diaphragm, it's not that sensitive to temperature. So it's very robust to temperature. Again, because you're now playing with only one variable, you're looking at only the distance and not any intermediary, like for the thermopile sensor, you find it has a very fast response, and it also, therefore the accuracy is going to be better. So the only way you can calibrate this is by having a sensor that that has a direct response correlation to pressure as compared to the other one. Okay, so now for the capacitive, you see they are gas independent. They have high accuracy, they have high stability, excellent linearity, as I was telling you, that established relation between pressure to measurement is direct to each other and easy to establish traceability to SI. One might ask, since it's a transfer standard, how would you calibrate it? There's some other methods of calibrating the reference standard, that is the capacitive diaphragm gauge, that involved some monitoring the ionic changes in a particular vacuum chamber, so which will be subject of another discussion. So now, this is the architecture of the capacitance diaphragm gauges. As you can see, what I was telling you, you have the low vacuum inlet and the high vacuum inlet. So for the high vacuum inlet, the sensor is actually built in a way that pressure is there is no air. Air is completely evacuated from this region and then sealed, okay? So then you have this other region that provides the connection, okay? So the low vacuum inlet, basically what will happen is, as the air is being sucked out in that manifold, you are going to have this particular plate bulging or deflecting based on the distance, the direction of that pressure outflow. So by that plate deflecting, what you're playing with is the distance of that particular sensor. And that D is actually going to give you a change in capacitance, which now by signal conditioning circuits, you are able to translate it back to pressure. So what you'll be noticing is we are moving from mechanical energy, which is the pressure, to electrical energy, but then for you to get an output that a human being can be able to understand is convert it back to the mechanical units that you're able to understand. So now you have the gap, which now provides for the permittivity and the silicon substrate. Then you have the insulation layer, as you can see from that point, and then you have the fixed electrode. So now, only in this capacitance, as you know, any capacitance is determined by the distance from the distance of the plates from each other. So we have the fixed electrode, but then we also have the one that is able to move from one point to another due to the deflection of that plate. So this is basically the architecture of the reference standard that we are going to use. Okay, so now the proposed calibration framework, of course, it will be involving a common vacuum manifold, a turbomolecular pump with backing pump, which basically is the one that's going to generate the vacuum pressure. Then you have the diaphragm, which is actually acting as the reference standard, and the thermal vacuum reference sensor, which is actually the unit under calibration. Then you have isolation valves for pressure stabilization and also for safety in case maybe the turbo pump does not behave. And you also have the high resolution voltage acquisition system, which basically is just a way of signal conditioning the signal from the electrical signal you're getting to a pressure unit that you can be able to easily interpret. Now, we are going to look also at the pressure step method and the calibration model. Basically, when I'm talking of pressure step method, is under very low pressures, when you're looking at around 0.3 Pascal, normal metrologists, usually space the measurement points equally. But under this measurement method, you'll find that direct correlation between vacuum pressure, and the measurement is not going to be possible to allow for equal distancing. So what basically we use is the algorithmic spacing method that we are able to determine the particular point, so that as under low pressure you can be able to do your measurements accurately. So these are a calibration model for the P equals to 0 to show the correlation between pressure and the voltage. So for the considerations for uncertainty, we have these: for the uncertainty of the reference, the fitting, the repeatability, the temperature factor that comes into to effects of temperature resolution, and also the drift. So what are the impacts? Accuracy, residual, determination, traceability to SI, confidence in vacuum pressure measurements, and reducing uncertainty in absolute pressure. So for the conclusion, a traceable calibration framework for thermopile vacuum reference has been proposed using diaphragm gauges, defined a structured calibration model, and establishing uncertainty evaluation methodology. Thank you.
Thank you so much, Sylvester, for the nice presentation. I think let's give him a round of applause for having presented very nicely. For the next presenter, please try to calibrate your time before you step here. So I think Sylvester was trying to give us the architecture behind the thermopile vacuum pressure, how it helps the temperature sensitivity, and also about the capacitative diaphragm gauge. So this helps us in how we can work on our pressure gauges. How do we make sure our pressure gauges also work well? So the next presenter is going to present on the role of temperature measurement traceability in enhancing consumer protection. A case study approach is going to be none other than Richard Odak. So please, the stage is yours. Let's welcome him by putting our hands together.
You wanna go faster, 1545. See to come through, see stress my guy. 0023. Come through if you know what that means. She can number 20023. Slide through if you know what that means. She got 023. Okay, your code better pay. Fika standard 2002. Slide through if you know what that means. She got 023. Okay, your code better pay. Fika standard 2023. 2023.
Bana 20023. Anakuchaja ni 00 fee. Clean deal kama dunge white here bit. Study non biz lazima confirm ni real. Wajibika signal control quality. Na bomba caps you go in heavier than quantity. Certified strong study unachiki solidity. You got the gadget no guarantee. Kona bululu na finya 20023. Na kiga look na nya caps imeti.
Okay. Good afternoon. Good afternoon. My name is Richard Odak, head of Temperature Calibration Lab at Kenya Bureau of Standards. Today I'll be presenting on the role of temperature measurement traceability in enhancing consumer protection, a case study. The theme of this year's RMC was mainstreaming metrology in health, manufacturing, and trade to enhance consumer protection. So what I did with this paper was to examine the role of measurement traceability in enhancing customer protection using case studies drawn from the activities of the KEBS Temperature Calibration Lab. By analyzing calibration data and technical engagements with customers and partners, the paper demonstrates how mainstreaming metrology strengthens confidence in measurements across health, manufacturing, and trade. So for the sake of time, I'll also try and answer some of the questions which I know are going to arise as we continue. Yes, I started my study backwards. I started with a conclusion and then tried to collect the data to reinforce my position. Yes, this is not the way to go about it. And yes, my results did indicate that that was the wrong way to go about it. So I know the question is coming, so we will see. So what was the background? Traceability alone is insufficient if uncertainty is not properly evaluated or if calibrated instruments are not used correctly. A complete measurement system therefore requires traceable calibration to national or international standards, validated methods, proper evaluation of and reporting of measurement uncertainty, and competent use of appropriate sensors in the intended application. Essentially, what I was trying to do was quantify the effect of not doing your calibrations properly, because that's another gap that we have. Yes, there are people who do calibration for the sake of meeting whether it's regulatory requirements or accreditation requirements, but then do not properly interpret or apply those results. So I was now working towards collecting data that could show evidence that just calibrating alone was not enough to say you sufficiently implemented metrology. So the methodology, again, was a case study approach. My sample size was very small because, again, I only sampled from customers that I had dealt with directly within my temperature lab, so there was that bias. And also it was a very small data set, so let's use this as a proof of concept for the idea I was trying to put across. The methodology was interviews and analysis with select temperature calibration customer records, including reported values, uncertainty and conformity decisions, qualitative assessment of recurring technical issues observed during calibration services and lab engagements, including uncertainty estimation practices and sensor usage, and then synthesis of these findings across health, manufacturing, and calibration lab context to identify common themes in consumer protection indications. So my first sample, I have not identified where I obtained the samples from, but I just basically called some of my customers who were in various fields. So because the RMC theme was related to healthcare, manufacturing, and trade, I looked specifically in those areas. So one was from healthcare. The example that we were using for case number one, clinical thermometers are typically calibrated at or about 36 degrees Celsius for representative devices. So for this particular client, being a busy outpatient clinic, they said each thermometer is usually used for about 40 to 60 patients per day. So assuming an average of 50 patients per day and approximately 250 working days in a year, one thermometer could influence the measurements of about 12,500 patients annually. In a data set of 10, I again asked him how many of these thermometers would they consider a critical failure if they're out of commission, either through breakage or through failure. They told me if 20% of them were not available, then they would have to shut down the clinic until they were able to access them. So then we were supposed to recalibrate a sample of 10 and see if we could identify 20% of them as being out of calibration, is the same as them being out of commission, and then it now helps us to go back to show how, for each instrument, how 12,500 patients could be affected. However, as you will see from my results, we had a perfect set of acceptable results. So for anyone who has done calibrations of large batches of equipment, you know it's not common for all the equipment you test to pass. We had because what I was trying to demonstrate from this study is that if you don't properly implement quality practices besides just calibration, you will have deviation in your results. Unfortunately, I sampled a clinic who had perfect performance. So all of them were within compliance. So I moved on. We looked at refrigerators, particularly those for storage of vaccines. A typical, now again in the same case, a typical vaccination storage for this medium-sized clinic would hold about 2,000 to 5,000 doses annually. And if temperature bias causes exposure outside of the recommended 2 to 8 degree range, vaccine potency would then be reduced. So again, given their sample, they said if more than 3 of their fridges were out of commission, it would mean a catastrophic failure for which the clinic would have to be closed down. So extrapolating from an average of about 3,000 doses per fridge per year, this would mean roughly 9,000 vaccines being exposed to potency reduction. So if one fridge operating outside of acceptable limits would lead to a spoilage of even just 5% of the stored vaccines annually, assuming 3,000 doses per year on an average vaccine cost of approximately 500, the annual loss could be estimated at about 75,000 per fridge. So if we had a failure of 3 of our fridges, the total expected loss would be at about 225,000. But again, because I had a very small sample size, all the fridges I sampled passed calibration. So I could not then show him, you see, based on your results, you have failure because all the fridges we tested actually passed calibration. So I have a theory, but I don't have the data to show that failure to calibrate properly will result in damage. So I moved on to manufacturing because I'm like, maybe these hospitals are implementing very high standards. Because again, and I know Dr. Njiru is hearing me manipulate my study, and he's very stressed for my methodology. I was looking for evidence to back up my theory, and this is evidence that doing it that way is the wrong way. So the lesson has been learned. But now I went to manufacturing to somebody who I know is a bit more relaxed in his implementation of quality requirements. And for this particular customer, temperature deviations could affect product quality, in this case, particularly affecting heat treatment and plastic processing. In their case, a heat treatment oven that was 1 degree outside of the specification would produce inconsistent metallurgical properties, leading to rejected batches. So for this small manufacturing line, they said that the approximate value per production batch is about 500,000. So even one rejected batch from poor temperature sensors would result in a cost implication of about 500,000. So as we continue to discuss, if you have a rejected batch, including all the other factors that go into recalling, correction, retesting before they can go back to production, they said it would cost anywhere from 500 to about 1.5 million. So now when we sample the sensors here, and you'll notice as the study continues, my methods are becoming a bit more open-minded. Even the number of data sets become larger. So I was sampling previously 10. At this place, I actually sampled 30. I've not shown all of them. But now in this case, we now have a bit of a deviation in our results. So I can now confidently tell this person that you are risking losing about 1.5 million based on what we experienced from sampling their calibrations. The issue here was, again, this is somebody who is implementing a proper quality system. They have all their instruments calibrated, but they are not interpreting the results of the calibration once the calibration is complete. He's given a calibration certificate with correction factors, with uncertainty, but because they don't apply any of these findings to their results, it was resulting in deviations at every other sensor. Almost 50% of their sensors were failing upon retesting. So what did I conclude from this study? I was hoping to have it very clear that calibration just by KEBS was a very obvious indicator of a disparity in quality between us and industry, but it ended up being that most of the industry was implementing very high level of quality measurements, but it did help us identify some of the potential sources of risk from some of these customers, including incomplete traceability chains, underestimation of uncertainty, and lack of understanding of sensor behavior in real-world applications. So addressing of these issues would require not only technical calibration services, but also capacity building and stakeholder engagement. The findings also help to illustrate that mainstreaming temperature metrology requires alignment between technical practices and regulatory frameworks, because it's not just enough to be implementing the technical requirements, but it also needs follow-up to make sure that implementation is effective. So this would mean clear requirements for traceability, for uncertainty, and especially for competence to ensure that measurement results are fit for purpose and defensible for customer protection contexts. And by embedding sound measurement practices into routine operations and decision-making, metrology becomes a practical tool for protecting customers, supporting compliant manufacturing, and enabling fair trade. The full details of the study, all the data, all the analysis will be shared in the full paper. Thank you.
Thank you so much, Richard Odak, for the nice presentation. Please let's put our hands together for the nice presentation from Richard Odak. I think Richard Odak is trying to give us how we align calibration with the management, the quality measurement, because calibration alone does not mean you get accurate result without managing your measurement or without following quality management into practice. And then also capacity building of stakeholders matters, because not everyone knows about the temperature or thermometer calibration unless you also have to engage into like capacity building, give them some awareness about this. Now, our last presenter is going to present on the precision for protection, advancing measurement practices in the energy sector. Is none other than Irene Kichohi. I don't know whether I pronounced the name correctly. So let's put our hands together as she is approaching the stage.
Fika standard 2023 20023 20023 yeah, owners are pattern for free. The quality is everything you need, and it's a different frequency. Yeah, in the Kazana Namboka, what game new deal now my squad. Yeah, I'm trying to tell you
all protocols observed. My name is Irene Gishohi from Kenyan. I'm a principal engineer. I'll be presenting to you on precision for protection, advancing measurement practices in the energy sector. So first, I need to tell you about our company. Kenyan is a leading electricity generating company in East Africa. We have an installed capacity of 1725 megawatts. And one of our strategies is to provide affordable power by creating value for shareholders while expanding energy sources and revenue streams. So our core business is power generation. We do have hydropower plants, geothermal, wind plants, and thermal. And we also do some consultancy work in the geothermal fields. We do some exploration, we do some drilling, and in part of our operation, we do have a calibration center where we do in-house calibration of our measurement instruments. So why precision matters in the energy sector? In the energy sector, we obviously have the grid, and in the grid, we have the generators, who are people like us, Kenyan and other IPPs. Then we have the consumers. The consumers, we have industries, we have hospitals, we have households. So, and at the middle of it, we have the national control. Their work is to look at the frequency and voltage that's in the grid, and their work is to balance it. If there is too much generation, the frequency will go up, and this leads to problems. Or if something happens to the grid and there's a fault on the consumer side of it, we lose some huge load. That leads to there's low demand, and there is higher generation, which will bring some imbalance. So we normally have people sitting at the national control. Their work is to look at the frequency and to look at the voltages. So we need precise frequency measurements, as this makes them decide, are we increasing generation? Are we reducing generation? Are we shutting down some customers? That depends on how it operates. Another thing on why precision matters in the energy sector is if the controllers don't manage the frequency, that will lead to a cascading effect where we will they will open breakers and people will lose supply. If they can't manage it beyond a certain frequency, it will end to the whole system having a total blackout. We've had this in Kenya quite a number of times. If we are not looking at the measurements, since we are dealing with very high voltages, that could lead to people getting hurt, people can get burnt. We're dealing with very high currents, could lead to death. It could lead to damage to our equipment. And now anytime we have, so that shows you why we really need the measurements, because depending on what the instruments is measuring, we make decisions. If a line has been isolated for somebody to come do maintenance, the first thing we do is to come to the line and we measure, is there any voltage? If it reads 0, it's safe, you can touch it. So imagine if you came to a power line, it's supposed to be 11,000 volts, you come and measure, it tells you it's 0. And yet it's not 0, it's 11,000, then you touch it. Imagine the damage, what could happen, yeah, in that situation. So anytime we have a system disturbance, this is where we have like either it's a partial blackout, we've lost a part of the grid, or if it's a total system shutdown, we need to come back to our systems. In our systems, we have the field measuring sensors and instruments that collect the voltages, the speed of the machine, the frequency, the currents, all that. And we need to analyze, because we need to see how did the machines respond. Because on a normal day, if the grid loses some of the load, okay, we lose some of the customers, the frequency will first go up. And it's up to the generators to regulate themselves by either reducing the load so that the frequency comes back to 50. 50 is the ideal state. So we need to, every time there's a disturbance, we come back to check on how did the machine respond. How did the frequency go? What was the speed of the machine? Did some breakers open? Did some not close? So imagine if we were doing that analysis based on data that is incorrect. That would make us make decisions for future operation of our machine that's incorrect. So we really need to have very, very accurate data to make this decision. I'll give you a case study for Russia. One of the power plants called Sayano-Shushenskaya. So it's a hydropower station. They have 10 machines, each at 600 megawatts. And for hydropower plants, they're designed, there's a band where they operate, it's a nominal range. If you go beyond it or if you go below it, there's too much vibration. So what happened in this station at that time, it's the other machine, they normally have one machine that regulates the frequency. So if the frequency is high, that machine will deload, so that's to bring the frequency back to the nominal. So that machine was out on repairs. They had to depend on this one machine. It was a unit 2 machine, 600 megawatt. That machine, the allowable band is between 0 to 265 megawatts, or between 570 to 640. At that particular time of the accident, the machine was at 475 because it was regulating the frequency in the grid. And the vibration that was noted at that time was 0.84 millimeter. That was the displacement. And it was 4 times higher than the other machines. But not due to them not having another machine to rely on, they were operating with this unsafe band. What happened is, due to the very, very huge vibrations, the turbine, the vibration was too much, the bolts could not handle it, burst open, you're dealing with a hydropower plant, and it flooded the power plant. It led to 75 people died. A few people who had made the decision to continue running the machine even with the high vibrations, they were sentenced to jail. And as you can see the photo, that's such a huge machine, because the people are, this is the size of the person. I don't know if you can see my cursor, versus this huge, this is the stator, this is the turbine. So you imagine such a huge machine. Obviously the penstock is the pipe that brings in the water is so big, and then it floods the station. Obviously you can't outrun that much water. So this shows you the importance of taking the measurements. They need to be precise and making decisions based on those precise measurements. So accurate data ensures that operators understand the true plant conditions. The maintenance people can work safely and they're not in danger, whereby you're being told a line is dead, you go measure, your equipment is telling you it's dead, you touch it, it's 11,000 volts. It ensures that you do correct isolations, and it ensures that you have emergency alarm functions, and you adhere to the function of it. Every precise reading protects a human being on the ground. So common mistakes that happen with inaccurate measurements, this could lead to delayed fault detection. If in our power system, we normally have protection relays that rely on data that comes from, so we have instrument transformers that they send you the current measurements. Based on this current measurement, if it shows you that the current measurement is high, the relay is supposed to open breakers and open the circuits, generally, open the circuits. If imagine if that instrument transformer is not giving you, it's giving you delayed or wrong measurement. You'll not be able to open that circuit in time, which could lead to fires. It could lead to equipment overloading, and overloading over time deteriorates the insulation of our equipment, so reducing the life cycle of our equipment. In cases of factories, it could lead to boiler explosions, premature component failure. You know, if there's maybe too much vibration, the bolts and the bearings, they could lead to failure. You could have inefficient system operations whereby you have breakers opening when they're not supposed to open, or you have them closed in an event where they're supposed to open. And due to the incorrect data, you have the operators not responding as they should based on the correct data. So the strategies that have been put in place to ensure that we have correct measurements is we normally have regular calibration of all the field instruments as per the maintenance practices. We do testing of our equipment, and then our standards are taken to like KEBS, the NMI, just to ensure that we have traceability and to ensure that all our instruments are reading as they should. Then we have standardized measurement processes, so that every time we are testing, if we are testing a flow meter, every time we make sure it's something that's procedural, done the same way, and it's standardized. Then we need data validation to make sure that whatever data you're reading, it's been validated and analyzed as it should be. Then we normally have continuous training for our staff to make sure that they know how to test the equipment, they know what this reading means, how it can affect the machine itself. If there's too much vibration, you're affecting the bearing. If there's too much temperature, if the temperature has gone very high, you're affecting the insulation of this. You know, we need to be trained on what this data means, how it affects, how you should react to that data. And then we have integration of redundant or cross-checking sensors. Like you could have a pressure sensor and a different sensor that's cross-checking that. So if one fails, at least you have a backup for it. The technological advancements that are in place, we normally have very high fidelity digital sensors that have very high digits. So the precision is very high. It can measure up to several decimals. For the very important signals that need to trip a machine, they're connected to the GPS, and it can measure time up to milliseconds. And now we want to move to microseconds. Then we have IoT-enabled monitoring equipment, whereby they're collecting data, and from all this data, analytics is going on to be able to predict how will this machine operate, how will it, predict whether it's deteriorating, when you need to do maintenance. That's the same with the AI. It gives us patterns so that we can be able to forecast and be able to do condition-based maintenance. And then we obviously have SCADA systems where the field devices are sending signals all the time, so we are able to monitor the data accurately and make decisions based on the data. So the future towards a fully data-driven energy system, we need real-time measurements, which is happening in milliseconds. We need to move to microseconds. Predictive models, which we are currently doing, though currently it's still very expensive because you need very many sensors for you to be able to do the predictive condition-based maintenances. Then you need autonomous protection systems so that they act independent from the control system. If the control system doesn't work, it acts as, on its own, it will be able to detect this current is too much, there's a problem, let's open the breakers. And then we need to have integrated worldwide measurement ecosystems so that in the grid where they're monitoring the frequencies, they'll be able to see this frequency has gone outside the band, let's start opening this load, depending on how they've cascaded the loads, which one to be opened first. So in conclusion, precision in measurement is the foundation of safety in the energy sector. It could lead to death of people, our equipment could be damaged, could have a blackout, which which results in loss of revenue for everyone in the nation. Then it protects equipment, people, and the environment. Advancing measurement practices is not just a technical improvement, it is a commitment to operational excellence and safety. Thank you very much.
Thank you so much, Irene, for the wonderful presentation. Let's give our hands together to Irene for the wonderful presentation. I think Irene, we know the importance of power and how we measure power precisely, and such that we don't encounter some issues. So the issue of safety and then reliable decision making when we measure our energy precisely. And also she also elaborated more on the inaccurate measurement accuracy that delays fault detection and boiler explosion in factories. So all these matters in our daily life. When we are doing measurement, we need to measure it precisely such that we don't encounter any issues. Up to this juncture, allow me to call upon Isaac Sunday to come and continue with the rest of the program. Thank you so much for having me at the podium. Call me Emmanuel Atari Simplicio.
If you know what that means, she can number 20023. Slide through if you know what that means. Your label, she got 023. Okay, your code better P. If you can standard 20023.
A round of applause once again for Emmanuel Atari. So when the program came out, we were informed today, the second day is the South Sudan to share this important event. So one of the things last night when it was still far, I was actually not worried. But yesterday, in the evening after the first day, I was like, what is going to happen tomorrow? Now this is going to be South Sudan Day. We have to make it lively because we heard the time that we don't need to make this event boring. That we need to make the event should be lively and everything. So I tried to look at what can we do. I asked Emmanuel Atari, what can we do to make this lively? So we tried to brainstorm. It didn't work. That was the time I decided now I need to contact AI. What can I do? So at that moment, the AI actually disappointed me. I slept at 2 a.m. And that's why now the mood is like this. So to do this, now I'm a scientist, but there's a phrase when a judge, when there are juries and the convict is somewhere, they say when people are going for recess that the juries should now go and stretch their legs, but they have to remember their ammunitions. So let me say the same thing to everybody who is here today, that from morning up to now is the right time to remember your ammunitions and ask questions as the panelists are on stage. So that's what I can say. Now is the right time to actually bring on the stage the panelists. We will, but what we do, we have to clap, say that the other people from the other room have to actually hear that there are people inside here. I've been hearing them, but they are not hearing us. I don't know what is the problem. So when we call a panelist on the stage, we have to actually clap very well. If you guys, yours is not soundful, I will add mine here. So welcome the first panelist on the stage, Dr. Henry Rotich, the AFRIMET Chair, and the Director for Metrology and Testing, Kenya Bureau of Standards. Welcome on the stage, sir. I didn't hear it. Come on again. The second panelist on the stage is Dr. Joshua Injiru, HOD, Research and Development, Kenya National Bureau of Standards. And the third person that is coming on the stage is, now we need to show him some love, and we need to increase the volume. Somebody in my country was actually want to pronounce the volume, but what he did is say increase the velocity. So now what do? We show some love for Dr. Leon Chow, the NIS representative on the stage. Dr. Leon, you are highly welcome. Come on, he's not yet on the stage. The first person is Dennis Osheng from Kenya National Bureau of Standards. Please, Dennis, you are highly welcome. Put some hand for Dennis. Come on. I'm trying to tell you it's real. Our sixth person is Sylvester Memia. Put some hand for Sylvester. Watch how I put it 2 by 2. Nick on a crew, now I'm chilling with the real ones. Yeah, I light it up. Basi soma hiyo lebo 0023. Tumakoda kikisha guarantee. Usipate umepima maji. Usipate umepima maji. Single standard. Our last panelist is Warren Kibenge from Kenya National Bureau of Standards. Warren, you are highly welcome. Put some hand for Warren, please. Come through if you know what that means. She got number 20023. Slide through if you know what that summer your label. She got 023. Okay, your code but a pin. Fika standard 20023. 20023. Double check, maybe go on moody. Double check, I jack and yak waki doko. Check, kiko poa inafai kuwe soko. Usiwanda usibaki gizani. Kaa ukijua rada ni gani. Usiwe na wasiwasi na nini. Tembea kama umejia, nina nina. 1545 with the confirm. One time with the photo what you really want. What you prefer. Press 20023, you can't do anything. 1545 with the confirm. One time with the photo what you really want. What you prefer. Basi soma hiyo label 0023. Tumakoda kikisha guarantee. Usipate umepima maji. Usipate umekupima maji. Single standard. Ya quality. Usipate cheki kwa mahasla. Fanya you wanna go faster. 1545. See to come through. See stress my side. Your label 0023. Come through if you know what that means. She got number 20023. Slide through if you know what that summer your label. She got 023. So we welcome again our panelists on the stage. Can we put a round of applause for them once again?
Unaweza shtuka na hii lifestyle juu ya standards na energy balance. Niki step in muad wa queen gallants. Fire in the booth wana nickname makrala. Kwa bona tonight I wasn't born last night. Sijaribu kufit na sijalika stuff fitting. Napewa allowance come hest just for
code hakikisha guarantee. Usipate umepima maji, usipate umekupima maji, single standard ya quality. Usipate cheki kwa mahasla, you wanna go faster faster. 1545, si tuta come through, si stress my guy.
That was 023. Come through if you know what that means. She got number 2. That was 023. Slide through if you know what that means. Summer your label. She got 023. Akai your code better be. Fika standard 2. That was 023. 222. That was 023.
Yeah, tuna David to halal kwa streets kagua mali through 2023. Anytime uko na shopping spree, fanya quality control kabla uchukue receipt. Another day another risk to take. 200k ndo nipande kwa stage.
So I am comfortable actually to stand. The last person we will call on the stage is Mr. Richard Odak. Put your hand together for Richard Odak, please.
Basi soma hiyo label 0023. Tuma code hakikisha guarantee. Usipate umepima maji, usipate umekupima maji, single standard ya quality. Usipate cheki kwa mahasla, you wanna go faster faster. 1545, si tuta come through, si stress my guy.
Basi soma hiyo label 0023. Come through if you know what that means. She got number 2.
So the audience, in Lao language, you are now the juries, and you will be asking the questions to our panelists. We learned a lot today from every one of them who actually presented this afternoon, starting from morning. So one of the key takeaways that will go with us is our EAMET chair, Dr. Henry. In the morning was telling us that without measurement, there is no quality. Without quality, there is no trade. And he actually explained to us what happened when he went to check his blood sugar, and the people in the clinic got it wrong. And if he was a member of the community who is not informed about accurate measurement, he would have actually be taking blood diabetic pills by now. But because he's one of the informed member of the society, what accurate measurement means, he has to go and retest somewhere, and it will actually confirm that his blood sugar is normal. So now we will give the chance to the juries, who are the audience, the participants from every corner of the East African community and other part of the world, to be asking the questions for our panelists for a better understanding about why we are here today. Now the theme of our metrology conference is all familiar to all of us, and is mainstreaming metrology in health, manufacturing, and trade to enhance consumer protection. We need to sensitize people. We need to protect our consumers. This is the reason we are in this hall today. I think either a chance for each one of you to give a brief overview, or we just go straight to the questions. Yeah, now we go straight to the questions, because I will be asking them questions later on, but not now. Thank you very much.
Okay, thank you. My name is Juma Nicholas. I'm coming from Mombasa Cement. And my question goes to the director, Rotich. There is time you said that you are providing us with the PT test samples. So, and from my note, is as if that is coming from, is an idea from EAMET. So, is this PT test, for example, for cement, which started last year, is it distributed to all labs in East Africa, or is only in Kenya? And if it's in Kenya, what happens to the labs which deviate from the results that you have? What do you do about that? And because the PT test itself is in cement especially, is tailored on major on the 7 days or 2 days, that is strength development in the curing stage, and 28 days, and also the initial and the setting time, as well as a chemical component, which is basically chlorides and sulfite, that is sulfate content present. So my question is, what are you doing about the elemental composition? Because you mentioned that we are buying the SRMs from the NIST, which is very good, but now considering the technology that we have and the labs that we have, because if it is from NIST and I have to calibrate my XRF, I have to use fused bead technology. But if I'm using the pressed pellet, that is SRM from the NIST, will only guide me in the wet analysis. So what are you doing about the elemental composition? For example, that is a silicon oxide, silicon 4 oxide, as well as aluminium 3 oxide, iron 3 oxide, as well as calcium oxide, so that I can be able to calibrate my XRF using the SRMs made in Kenya. Thank you.
Yes, my question goes to Dr. Henry. We learned this morning, as he stated, that he went and tested his blood and found that there was different testing. I just want to ask simply, in other partner states, we talk about traceability of the equipments and calibration of tools of health sectors, but in some partner states there is still not yet calibrating, or they have no traceability of all this equipment. What advice can you give to those partner states who have not calibrated those equipment in the health sector?
Yes, good evening. Yeah, my name is Joseph Kadenge. I have 3 simple questions here to 3 different presenters. My first question goes to Dr. Leonie Chow from NIST. Yeah, big up for your good presentation on the new realization of the kilogram. Now, my question is, from 2018, of course, there is a new definition of the ACI unit. For instance, in your presentation, you showed us the definition of mass, the kilogram from the prototype in Paris. Now we have a new definition, which is, of course, defined from the calculations of the mass using the prime constant in the Kibble balance. The same applied even to thermodynamics, the temperature, Now we are moving from the fixed point cells. Now we are using the first principle, Boltzmann constants. Now my question is, how possible for African countries to achieve this, the Kibo balance, the equipment for realization of the Kelvin and the other SI unit? How possible for African NMYs? My second question goes to the president of EAMET, Dr. Lotich. I remember we were together in the EAMET in Ghana, and today, of course, in your presentation, you told us the partnerships with the other international NMYs to capacitate our African NMY. There is a project, of course, EAMET entered with one of the Metrology Institute in China. And most of these partner states, of course, got the forms to fill, and they appointed some people to attend that training, I think, in China. I wanted to know from you, what is the update of that training in China in order to capacitate our NMY, especially in our region? And my last question goes to Odak, my friend in temperature. He showed us the case study of temperature measurement, especially for clinical thermometers, refrigerators. I'm very interested with that research, and I saw your results there. You showed the decisioning. I saw all the measurements are accepted. Now, if you consider the standard, ISO 17025 of 2017, of course, the standard have a clause for decision law. And I saw the application, I think, of that standard in that result. Now, which criteria do you use now to give that decision, Mr. Odak? And if that criteria come from the customer or from the standard, or you created your own criteria to judge that result? Thank you very much.
Thank you very much. I would like to thank you for all the wonderful presentations. My name is Simon Rashana, and I work with Measurement Solutions in Uganda. We are a calibration lab and a medical equipment supplier as well. So I would like to, my first question goes to the gentleman who presented on the STM32 based magnetic stirrer. Your presentation was good. However, what I noted was that you did not talk about the homogeneity of the sample. You see, as you stir something, I would wanted to hear a relationship between the efficiency and the homogeneity, because you're stirring something so that it mixes properly. I would like to hear something on that. Then I would like to talk to address my brother Richard from the temperature lab. You see, the vaccine refrigeration equipment, this is a comment because I'm a supplier of this equipment and an agent of one of the leading manufacturers, B Medicals. This equipment usually has what they call an RTMD, a remote temperature monitoring device, whereby even from where I am sitting here on my phone, I'm receiving alerts if somebody in a medical center in Uganda forgets to lock a door. So in the same vein, when the temperature is exceeded, we keep getting alerts. So basically, your sample space was bound to get only acceptance, because each refrigerator with vaccines has that RTMD installed on it, and it also has an independent temperature data logger, which also streams data. So definitely, that's why the results, as Mr. Kagoma is putting it, had acceptable, because these people would, as Mr. Kadenge, is putting it, it has accepted, because these people would have already known before you came if there was something and the temperature was out. Now the challenge in this system, as somebody who works in this system, the challenge I would have wanted actually to present to this forum is that most of the equipment, medical equipment, vaccine storage, cold chain equipment, supplied to health centers across all our countries is usually procured by WHO or UNICEF. And most of them are donations to our countries. Now, the issue which has not been addressed in that system is the issue of calibration. Because, for example, most of this equipment has a warranty of 10 years plus, but there is no mention in the operating procedures that this equipment should be calibrated after this and this period. So I would like to challenge the member states to see how they can enter into that space and engage the Ministry of Health in the countries and engage WHO or UNICEF to see that that can be factored in within their framework. Thank you very much.
Okay. Okay. My question goes to Dr. Leon Chion. It was a very nice presentation about realization of kilogram. And as it was, you said that there are two methods or two ways. It works on two methods depending on whether static methods or dynamic method. My question comes from those instruments used on realization of kilogram. One is X-ray crystal density method. So do you still work on this type of realization using crystal density method? And if not, or if yes, between two methods, based on the Kibe balance and the crystal density method, which is the simplest one for African countries to adapt? Thank you.
Hello, I have one question and recommendation from Mr. Benson, the ones who were trying to address the matters of the flow meters. My question is that we are all understanding that there is some gaps in the legal metrology, gaps in firmware verification systems. And as of now, we are all knows that most likely flow meters, they normally use firmwares on controlling some of the flow which are passing through it. And also those flow meters, they have the physical seals in it, and yet they are still controlling the firmwares to monitor the flowing of the fluid through it. So my question is that how can we manage legally controlling the electronic seals within the flow meters that are normally using through the discharging areas in our oil marketing areas? And my recommendation is, another recommendation is, from your presentation, you address some few areas that we can use the master meters to verify the meter in use. We know that the master meters, it has got the correct meter factor, the same to the meter which is under test. What are the mechanisms which we can use together to establish authentications protocols to controls those factors which are normally used within those meters. My recommendation, I'll give it after the answer. Thank you.
Thank you, session chair. My question goes to Dr. Leon Chow. I appreciate your presentation that you addressed on advancement in metrology. You presented on the fact that we have metrology have advanced. Metrology is on the advanced stage now worldwide, and you actually presented different measures, Cabra or whatsoever, and you ended up on the definition of SI, of which we now use that to quote or to peg our measurements. But yesterday we had a presentation from CARBS, of which they presented that they do have the prototype standard of mass, of which they are keeping it up to the moment. Not only CARBS, I think different metrology institutes do still keep those prototype standards of mass, kilogram specific. Now, my question now comes that if there are still relevance of maintaining those prototype standards, having definition of SI in international standards of measurements. Thank you.
Yeah, I think we'll go to hear from the panelists for the answers, and then we'll come back again for some questions. Thank you. I think we'll start with Dr. Henry Rotich, please.
Thank you very much, Juma, Nicholas, for the question on the PETs. You asked us what we do on the PETs. I think maybe the one on cement, we don't have it at AFRIMET's level, but I know at KEPS we are working on that PET. That was to address some of the challenges that we are seeing in the sector. So as at chemical metrology, that's what we're doing. Now, you also wanted to know whether we are offering in the region or the other places. I think for the Kenyan one, we are actually working mostly with our industry, the industries which are manufacturing within Kenya. But so if somebody fails a PT, what is the purpose of a PT? It's not a death sentence. It is continual improvement. You remember? ISO 9001 advocates for continual improvement. It's for you to check your systems and see what you can do. So even at key comparisons, when you participate and you find your results strange, you also learn a lesson. So even a failure is a very good lesson. In fact, my friend Lubonga will tell you that when he was at NIST, there's a time he says he was crying because he worked the whole day and there was nothing. When he went to run the test, there was nothing. And his professor told him, no, in fact, nothing is a result. It's a result because it's one way of telling you how not to do things. So you learn. So when you participate in a PT, one of the things you might be very successful and have a very good set score, or you might learn a good lesson that will help you to improve next time. So there's no problem. And then if you don't participate this time, you can also participate the next time, because we encourage as many people to participate as possible, because it's meant for continual improvement. So you talk about the test. Of course, the chemical test, we have the primary methods, so the traditional methods that we are using, which is chemical, where you are doing, I mean, I don't know whether I should call it digestion or where you are breaking down and then you are doing the elemental analysis. Then a more way, so we can actually use instrumental methods where you are having the XRF, you can also use the AAS and maybe other methods which keep on coming. So that will also be good. And then for you to also know the performance, then that's where now you're doing the 7-day test. I just wanted to say this. I think in metrology, one of the things, especially in chemical metrology, we have a very, very important statement that we normally make. How far does the light shine? So you know when you have a torch at night and you light it on, sometimes you can mulika very far, isn't it? Or you can mulika very wide, isn't it? So in metrology, that's what we do. You might not do everything, but you can have a capability which actually demonstrates the competence you have that you can deploy in other areas. So you might not do everything. I think it's an aspect of Pareto principle, isn't it? That you look at the 20% that demonstrates you can do 80%. So I think that's what I wanted to say, that you might not do everything, but you look at those capabilities that demonstrates your capability to cover a wider spectrum. So we had a professor who used to teach us the most difficult maths, you could call it analytical what? In mathematics. And he used to say that if you have done that course, then you can do anything else. And just like this morning I was saying, if you are good in physics, you can become anything. You can become a mechanical engineer, you can become even a lawyer, isn't it? Because that's a foundation. Now, the other aspect on the issue of advice to give, that's from my brother from Sudan, South Sudan, on the aspect of traceability of measurements. I think when you look at some countries, they make it legal. They put it in the law that it's mandatory to calibrate all the medical devices or equipment. But as good practice, because when you look at a number of hospitals, you find they're accredited. So there should be that requirement that they should be able to demonstrate the performance of their equipment that they're using, especially critical equipment. So maybe the only advice I can give is look at your country. If there's no way, I remember one time we were working on the thermoguns when there was COVID, and we worked with weights and measures. We found that with us at the NMI, calibration was voluntary. But I remember we discussed with Wamwana and we said they have a clause in their regulation which we can write on it to ensure that people are calibrating those thermoguns. So it's good to look around and see where it is, but also encourage other regulators. Because when you look at the health sector, there's accreditation. There's somewhere you can ride on and they can be able to really uptake the issues of calibration. But what about at a personal level as a patient? Can you be able to ask whether their thermometer is calibrated or their PP machine is calibrated? Maybe it's your right to demand, isn't it? Yes. Now, on the other one, on the project that we were having collaboration with other national metrology institutes across the region, I think I mentioned in the morning that we've worked very well with NIST. We've worked very well with other NMIs, including the National Metrology Institute of South Africa, and we try to create opportunities for capacity building. On the China collaboration, which I mentioned in the last year, is that we signed an MOU, and that MOU was very strategic because this was MOU with the provincial metrology institutes in China. Changchun is one of the provincial metrologists in China. So remember, if you are to participate in the activities of the meter convention, you find that sometimes, I said we have 48 members in the AFRIMET, and only 8 of them are active in the meter convention. So now, working with these regional or provincial metrology institutes will create an opportunity, because we can have even some comparisons with them to help those other NMIs who are not also participating in the activities of the meter convention. So one of the things we got was the training opportunity. But you remember that training opportunity was for, I think, next year. I have followed up, but they will give feedback on that process. They are still processing. But we are looking out for other opportunities also. Thank you very much.
So, if I may also just add to what my director said, especially for establishing traceability, whether it's in health or it's in any sector. For you as the NMI, especially now that you know the importance of calibration, it's now your responsibility to spread that information. It may not be practical for you to expect everybody to be able to do it immediately, but the more you make people aware, the more engaged they are, the more likely they are to onboard it. So it may not be legally mandatory, it might not be culturally the norm right now, but like the gospel, once you know, you must spread it, and then eventually it will catch on. Now we have some questions from my brother, Mr. Kadenge. I know my colleague from NIST will also speak more to the first one in terms of how African NMIs may be able to achieve first principles. I can only speak for the ones which I know about. I know for temperature, ours is a bit costly, the investment, the kind of Johnson bridges used to realize the Boltzmann. In 2019, when our SI was redefined, outside of the Asia-Pacific region, who had made it one of their key goals to invest in lots of them, so they had about 6 in that region. There were only 4 in other regions in the world. So there are not a lot of that level of instruments, maybe for temperature, for example. But from us, I can tell you today, there is a prototype cable balance at KEBS being built, being tested. It's actually available. You can pass there. Dr. Mbati and his team have been working on it. So depending on the measurement, depending on the field, depending on how complex it is to achieve, there are some which are easier to achieve than others, and there are some which you can just look around. We have a cable balance in Nairobi right now, being prototyped, being tested. So some are achievable, some we just need to prioritize how we can get there. Now, in terms of the results that I got from my custody, how were the decision rules defined? The decision rules for this study were defined by the requirements of the user. Because I looked for the simplest denominator, again guided by both 17025 and I like guide G8, because especially for what I wanted to present for this study, I wanted the simplest common denominator for all the sectors I was going to test. So I said it's easier to use the end user requirements because all of them were within reason of what I was targeting to achieve. So that's what I used to select my decision rule. And then my brother Simon had asked me about the results from the fridges and how they were always going to be within tolerance. And now here I'm glad you asked the question because it highlights the need for this study, because yes, on your sensor it says 5 degrees and then it confirms to you 5 degrees. But how do you know that 5 degrees is accurate? Independent verification. So yes, the user is saying it's within tolerance, but now when I come with my calibrated standard and I compare my results to your results and these results agree, we end up with confidence in that result. Because yes, it's giving you a positive result. But it's like, I don't know if you've seen this meme of Obama giving himself a medal because he tested himself and found himself to be good. It's the same thing. If your system checks itself with no external verification, you'll be running a continuous loop not knowing if there's any gaps in your system. So yes, okay, my sample size was small, but it's still having that external, because it's something especially from 17025. We put a lot of emphasis on validation of results using intercomparisons. One, because it has the most dynamic data analysis, and two, especially for NMIs, it helps us publish CMCs. But there are other proposals in that clause that we usually skip over. Recalibration of retained samples, comparison with external samples, intra-laboratory comparisons. All of these are usually within the same clause, but we always jump to 772 that talks specifically of intercomparisons. So it's also important to incorporate some of these other methods of method validation just to add more confidence, because we say calibration is about confidence. How thoroughly your results are vetted, how well they're analyzed, gives you more confidence in the result you get. So when we say I have 95% confidence, is because you put in all the factors you expect to give you disparity, and when it's still within your accepted limit, then you have the confidence. So that's why I say, in as much as it has external monitors which would have said they're accurate, me coming with my own independently calibrated sensors and getting the same results as theirs now gives confidence to their result and also validates their processes.
Hi, everyone. And to continue echoing the sentiment here about kilo balances, I believe the first question was how feasible is it for African countries to own a kilo balance? And my answer to that is it really depends. Question back to you is what is your budget and what is the uncertainty you're chasing? How many digits are you chasing at what mass level? So in order to just the raw materials alone to build the big kibble balance is probably 5 million USD, you know, whatever, like 100 times more in shillings, right? And even if I were to somehow magically be able to teleport that system over here, it's not push button. There are 4 people, myself included, that built the system, and only one and a half of us know how to turn it on. I don't even know how to turn it on. So I highly recommend not going that route of owning the big kibble balance, chasing 8 digits on a kilogram. America chose to do it because of international pressure to contribute to the redefinition of the kilogram. In order to achieve that redefinition, the rules of the game were you need at least 3 experiments in the world that were better than 50 parts per billion. One of them had to be better than 20 parts per billion. And then the last criteria, I think, was you need 2 different experiments, right? So because we had the kibble balance and the silicon sphere, this is what differentiated the 2 different experiments. So NIST went this route of going ultra complex, and then and now we're trying to make it more simple, more accessible. So the big kibble balance, it's not just the instrument itself, right? You need also an absolute gravimeter in the same room. You need this entire system to sit on a vibration isolation block. The whole room is a Faraday cage. You need an entire instrument rack that is taller than me. Voltmeters, current source. Yeah, you need both quantum standards also within reach. So both the quantum Hall resistor and the programmable Josephson voltage array, and then the list goes on. It's a nightmare to work with, but for us, again, it was necessary. Now, with that said, NIST has also started another project, which my colleagues are working on, which is a slightly simplified version of the big kibble balance. We can call it the medium one, which is also striving for 20 parts per billion uncertainty off of 100 grams. So the instrument's smaller, but I would not say it's much less complex. You still need all the quantum standards and everything. As soon as you want to do better than 1 ppm, you require all the bells and whistles. But we are with that project, we are trying our best to make everything as transparent as possible. I think the idea is to put all the drawings, all the blueprints online for open access. So anybody that can that has access to manufacturing capabilities can duplicate the system in-house. it will also be a very big challenge because that system is a piece of art. You have to know how to do all the alignments. There's a lot of wisdom built in order to get it to function. But with all that said now, the KIBG2 that I presented on, this is our way forward of showing, hey look, if you're not interested in national prestige of owning the world's best balance, if you're not chasing 8 digits and practically speaking you can do a lot of good with just 6 digits, the KIBG2 system is designed exactly for that. It's compact. We've made it, we're continually shrinking it. Total package including electronics and stuff, the raw materials puts us at about I think around the same price as a mass comparator, around 50,000 USD. We continue to pull that price down as well. I understand KIBG2 only goes up to 20 grams, but right now as we speak, there's a we're designing the next flexure system because the DoD is funding us to build also a tabletop system that can reach up to a kilogram. So between KIBG2 and whatever we call the next one, we should be able to span 1 milligram up to a kilogram with OIML F1 specifications. Yeah, let me think. So how to get at least one system over here of one of these tabletop systems. So our neighbors in Mexico, CNAM, which is the National Metrology Institute in Mexico, we recently have partnered with them. They've sent over 2 engineers. In fact, they're in my office right now learning how to build KIBG2. And once they have learned the intricacies of the system, how to assemble it, disassemble it, tune it, align it, they're going to take the full suite, the full system back to their lab. So that will be the first tabletop kill balance that can do 1 ppm, a few ppm accuracy that has left the United States, that has been deployed. And I think we can probably work out something similar with you guys. I can't promise that, but I was chatting with Dr. Ambadi at lunch, and it may be possible that maybe we can host some of you guys to come over to NIST and do the same type of exercises we're doing with the Mexicans right now. Maybe you guys can bring a system back here, 1 or 2 or 3, however many we can fund. Yeah, something like that. I believe the second question, and I'm dumb for not bringing a pen and paper like everybody else. I believe the second question was between the silicon sphere and the kibble balance, right? So I'm team kibble balance, obviously. The silicon sphere project, that was spearheaded by PTB in Germany, the Japanese, and the Italians. So coincidentally, the Axis powers of World War II. So those guys were team silicon sphere. I was like, it's too late for paper. I think the mass community calls the silicon sphere a pseudo primary standard because it's still an artifact mass after it's been calibrated with that method. In my opinion, it is easier to use because it's an artifact mass, right? You have it in your hands. It plays well with the current infrastructure. And if you're not chasing one of those the best silicon, which is like isotopically pure silicon 28 or whatever it's made out of, and you go for the cheaper version, I believe it's very affordable. Yes, it's a sphere. It rolls. I don't know how you guys deal with that, putting it on a balance. But I do think the kibble balance is the right way forward for 2 reasons. One is it is a primary realization using electrical standards directly tracing back to the new SI, and a non-technical clue is PTB is also now designing and building kibble balances alongside us. So unofficial quote is, I think they realized the kibble balance is still a better method. And right now, during this development phase, these kibble balances are very finicky, right? It takes a lot of alignment, you have your vertical gravity and all these annoying intricacies. But as this stuff, develops from generation to generation, and now because we have a commercial partner also working on this stuff, I think one day it will look and feel like a mass comparator system, whereas you just push a button and you walk away and it works. This KIB-G2 system is almost there. We just don't know how to turn it into, box it up and package it nicely and make it robust. So, pick your poison. And I think the last question was, how are we dealing with these artifact standards that have been that we've used for so long back at home, right? Was that the question? Okay. So the mass traceability chain, the dissemination chain right now, still completely relies on mass artifacts. The only thing that has changed is that the primary standard is no longer an artifact, but rather a machine. Once we use that machine to assign a value to a kilogram artifact, and then we give it to the mass enforce group, and they still disseminate in the traditional way by doing inner comparisons using mass comparators. So the best masses that we have are still all the platinum iridium ones that have a very long history. We've tracked the drift, we know its behavior. So those are not going anywhere anytime soon, and then still will be treated as our most precious way to, our most precious standards.
Thank you. The main primary objective of stirring a liquid is to attain homogeneity. Most of us, majority of us have been to the hospitals, have been given the syrup for the babies, and you're told, or for the adults, you're told before you take it, shake it well. The intention is to attain homogeneity. So in all our primary stirring processes in our research centers and laboratories or in metrological laboratories, we intend to attain homogeneity for the efficiency of the outcome. In most cases, in most areas, where, like I mentioned in the morning when I was presenting, where stirring is of essence is in the process of manufacture of phantom equipments for research purposes. Thank you.
Yes, so the question was about OMCs and after calibration, whether they adjust the meter. We don't know whether they will adjust the meter or not, and possibly they can adjust the meter. So for us as KEBS, we normally do calibration as a service. So it's up to the user whether they would want to adjust the meter after we've corrected it or not. But I know for meters that are used for commercial purposes, like as we discussed for the alcohol or the beverage manufacturing companies, like East Africa breweries, when they receive their ethanol, there's a KRA meter that is installed at the receiving point. KRA is our government agency that deals with the taxing of the goods in the country. So for purposes of VAT, the tax now to be paid calculation, there's a meter that is installed at the dispatch point or the receivable point. So the meter is enclosed and only reports to KRA. So there's live information being read at KRA offices to verify that the meter is working well, and it is often calibrated alongside KRA. So also for weigh bridges as well, because they are used for commercial purposes. When we are calibrating weigh bridges, we involve the Bureau of Weights and Measures. They will install a seal, a physical one. For the moment, for weigh bridges, we don't have any electronic way of relaying the information, or maybe having an authentication that is electronic, that cannot be tampered. So we only give a seal. So unless maybe when weights and measures go and check that the seal is not broken, the manufacturer or whoever's instrument is being calibrated, we will not be able to monitor that it has not been interfered with. So you also mentioned you have a recommendation for the process. Yes, maybe he can get a microphone.
Thank you very much for your good answer. Actually, you answer correctly based on what I understand. I have only 2 recommendations. Currently, there is we adapt the recommendation from OIML. It's called recommendation 137, and also there is another guide from the WellMec, guide 7.2, and also Canada. At the moment to speak, right now they are verifying the firmware, the software that control the measuring instruments. They have the guideline and regulations based on that. Maybe we can chip in and read those guidelines and regulations based on those the firmware that control the measuring instruments, on how we can verify them and control based on digital expansions. Because most likely firmwares nowadays, they control the measuring instruments. On how we can control as legal metrology is the gap. So those guidelines give us the highlights and overviews on how we can control and manage each and everything through the firmware systems. Maybe because we can exchange the contact from there, then we can see how we can narrow down the
Yeah, for sure. We can go through the guideline, and it will help us maybe develop a method for firmware authentication.
Sure.
Yeah.
That's really.
Thank you.
Thank you very much.
So now we will go for 2 to 3 questions for the second round. And anybody who is ready, whose hand is up, you'll be given the chance to ask the questions.
Thank you so much for the opportunity. And my question is to Mr. Warren Kibinge and also to Dr. Leon Chow. Looking back at what we discussed yesterday with regard to calibration and traceability measurements in manufacturing industry, specifically the food manufacturing industry, from Warren, I just wanted to know if computational fluid dynamics is a field that can possibly be applied in reverse food engineering methods towards designing process parameters, and is it also able to enable companies, institutions like NIST, which now again goes back to Dr. Leon Chow, to design or develop SRMs for such complex food matrices. And I'm talking about food matrices that rely on wild fermentation processes.
The theme of the conference is mainstreaming metrology in health, manufacturing, and trade. I've heard about, we have been talking about calibration, and we've been looking mostly about on the instruments. But on the chemical side, the decision that is made in the hospital, mostly when you go for tests, they usually go and take a blood sample, or they usually go and take a urine sample and whatever. Now, how do we demonstrate metrological traceability of those measurements? That question has not been answered through any of the presentations that I've had. And I want to ask the panelists if there's anyone who has some idea on how we are going to demonstrate metrological traceability in laboratory medicine. Thank you.
Good evening. Mine are not questions. There are two, just clarifications to focus inquiry to eliminate ambiguities. One to Mr. Odak on small medical devices like thermometers, which have their periodic service calibration normally prescribed in their small manuals insert. And again, some equipment periodic calibration, like the pipettes, depends on their frequency of use. Just like your case study that enumerated, you recorded about 40 to 60. That's a typical Kenyan hospital would record about that number. And in a case like this, what is the frequency or the calibration interval for this equipment? My next observation that I need a clarification is to Dr. Leon. As a staff of the body that promotes the usage of the SI unit, I would like to know why the kilogram is considered an SI base unit for mass, although it has a prefix kilo.
I'm Joseph Mahila from TBS. My question is going to Dr. Chiao. My question is, I wanted to know whether the electrical current flowing through the coil of the cable balance have the effect on the mass measurement.
Okay, you may answer those ones as we come to the end of the session.
Okay, I guess I'll start. I'll start by saying I'm even dumber for not accepting the pen and paper offer. I thought that was going to be it. The question about SRMs, I'm afraid I'm not even going to try and chime in on that. I know nothing about SRMs, so sorry about that. And then, oh my God. Can someone remind me what the second question? Yeah, that was the last question, right? Yeah, so, okay, I can answer the last question first because that's fresh. The effect of the electric current in the coil on the test mass, that is a valid concern, right? Because that creates an electric field. But the good thing is, in all the high-end precision kill balances we built, the coil is shielded inside of a permanent magnet system, which has an iron yoke all around it. So, for example, in the big NIST-4 kibble balance, right, we measured using a Gauss probe above the surface of the magnet, and it's so well shielded. I think a few centimeters up, you're dominated by Earth's magnetic field. So there's basically no interaction between the electromagnet and the mass you're weighing. So we are able to do stainless steel on it. In the small kibble balance that I showed on the slides, right, that one has a voice coil actuator, meaning that magnet design has no cap to it, meaning the magnetic field is exposed, so it goes all the way to infinity. And so we did the same exercise. We had to measure how far away before the magnetic field starts interacting with, for example, if we want to weigh a stainless steel mass, which is why the system sits about this tall, is because we have to put the mass this far away from the magnetic field for it not to be susceptible. So the next version we're designing, the design choice was because we wanted to build it with as many commercial components as possible. We don't want to keep designing all these, custom wound coils and whatnot. We wanted something commercial, and this is what was readily available. So we went from, we swung the pendulum, right? We start with everything is custom made, everything is super expensive, everything is a pain. And we swung the pendulum to the other end. Let's get everything off the shelf with as little modifications as possible. That also turned out to have a lot of problems. So in reality, we should be somewhere in the middle, right? We still need to be able to design a magnet system that is closed, but try and keep it easy to manufacture so that we can really shrink the balance down in terms of height. There's no need to really make it this far away. You remember the other question? Can someone remind me of the other questions? Sorry. Oh, about traceability to in medicine.
Dr. Chow, it was a clarification that I needed to know why the kilogram is considered as the SI base unit for mass, although it has a prefix kilo.
That's a historical question, and I want to say I'm fuzzy on this history. I believe the gram came first, and it was originally called grav, G-R-A-V. And then I want to say, and don't quote me on this, maybe you should ask someone who actually knows. I want to say then it became, from there they realized that we need something a little more massive. But the grav was already established, so they went with whatever the 1 liter of water at whatever, like 4 degrees Celsius or something, which became the kilogram. I'm very fuzzy on that. I'm just throwing out whatever's coming to my mind right now. And then metrological traceability in laboratory for medicine. I also don't know much about the applications of this, but I want to say probably the pharmaceutical industry uses a lot of these precision scales and mass comparators for measuring drugs. So I think it'd be pretty beneficial if, and I think they have to hire all these accreditation. In the US, they call it accreditation bodies, where these companies go to other companies to then calibrate their scales for them, and whatever else they need calibrated. So I guess wouldn't it be nice if your system could self-calibrate, right? In the middle of the night when no one's using it, it just runs its own little velocity mode, and by the morning time, it's been recalibrated. So maybe that would ensure that the calibration cadence or frequency is a lot higher than, let's say, annually or semi-annually.
Could you, Dr. Lovonga, kindly, could you bring up that question again, kindly? You know.
Yeah, the theme of the conference is mainstreaming metrology in health, manufacturing, and in trade. However, I have not heard anybody talking about metrological traceability in health. So I wanted any of the panelists to tell us how we realize metrological traceability in health, specifically in laboratory medicine. Thank you.
Like I've always stated something about phantoms. This is an experience I had when I was given opportunity by KEBS to be attached to Tubitak for some time. And they have several machines that they use to calibrate in health sector, like hematology meters, and some of the specimen they use could be not the direct ones. And that is why in the metrology section, specifically in Tubitak, they have a section called chemical metrology, where their main objective is to prepare phantom specimen to mimic exact human body parts, ranging from blood, skin, bones, for these calibration purposes. And these are what they're using as primary standards or reference standards for calibration of these machines. Thank you.
Maybe to add something else through the session chair, the question of Dr. Luvonga, the realization of the SI unit, metrology traceability in the test environment in the medical labs. Speaking from experience in my earlier years, I was in the medical sector in the Kenya Medical Research Institute in the pelvic inflammatory disease section. And how we were able to make sure that all our tests are traceable is in the correctness of the reference standard or the reference material. For example, the example that you gave on urine. You bring in urine, you're supposed to do a urine culture. It is not in your correctness of extracting and isolating pure colonies of that urine, but actually referring it to a specific standard that will actually tell you that specific strain is exactly what you're looking for. And that we could only rely especially on the standard, the reference standard that is in-house. So also the place of a certified reference material is very important also in the medical laboratory work. Thank you. That would be my comment on that.
Yeah, and I think when you look at, especially in the chemical and biological labs, there's a lot of focus on the reference materials. For example, if you look at NIST, I know they've done a lot, specifically on some of these SRMs, which are supported by the CMCs that they filed. So I think it's through use of certified reference materials, or maybe we are talking about NIST, those are the SRMs that they're using. Yeah.
Sir, Mr. Rodak.
But maybe Luonga, you also wanted to add something in that space, because I know you've handled that sector quite a lot. Specifically, like when we are talking about ethanol in water, for example, which is one of the things you did. So the certified reference material that you develop can now be used by the labs when they are doing their measurements, and they get traceability through the NMI that produce that certified reference material. Thank you.
Yeah, so the first question was on whether CFD can be used in manufacturing, and specifically in the food engineering process. From Evelyn's presentation yesterday, I gathered that there are some cases where you will use curing chambers or ovens for the biological, the bacteria you are producing, the probiotics you are producing. There's the term I'm looking for. So in those chambers, you would want temperature to be regulated to a certain point, before you begin your process, you can simulate that system in a virtual environment to see the distribution of temperature. And from that, you can conclude whether to initiate the process, the curing process, or whether maybe the temperature distribution will not be favorable for bacteria production. On the metrological traceability in laboratory medicine, from my section, I think the best we do is we offer traceability through the SI unit kilogram. So when we calibrate their balances, and from their balances now our masses are calibrated to the SI, the balances that will be used to measure maybe the quantities of chemical that is used in the system will draw their traceability, because probably they will be measuring in moles. I am not very conversant in but maybe mole conversion to kilogram, that can draw its traceability through the kg.
And I think he has explained very well, because why do we do calibration in the labs? We are disseminating the SI unit to the labs and also establishing calibration for them.
Okay, I would also like to answer the question by Dr. One of the equipment we usually receive is mainly to test for the syringes, especially the ones that are used in hospitals. And in that we have to check whether when those syringes are being used, can they introduce maybe the air into bloodstream. One way to do that we usually use is the absolute measurements, and one way we are able to provide them the traceability is by having accurate measurements in the absolute regime. And as I had already presented, that's being affected also by the way we measure the vacuum pressure. So an area that we actually related to in medical laboratories, providing that traceability, checking those syringes, that in case that while they are going to be using, they're able to trust whatever they are going to obtain, that it won't introduce any air bubbles in the water, in blood.
So allow me to answer your question on calibration intervals with a question, so that I can also expand a bit on the topic, because I feel like we do a lot of our calibrations legislatively, because we have to, and not for quality of measurements. Because why do we calibrate? Calibration is about establishing confidence in measurement. Because if you just want to strictly adhere to the requirements of a standard, you can apply whatever standard is in your field. If it's an OML standard, if it's an ISO standard, if it's an IATA standard. But why do we calibrate? There is no perfect measurement. Every measurement has a certain amount of uncertainty associated with it. So why we calibrate is to establish confidence in the results that we are getting. So if you know, based on the performance of this instrument, it's likely to drift after a certain number of months due to usage, or it's likely to drift due to inactivity, or it's likely to drift due to handling, or it's likely to drift due to mishandling, whatever the reason may be. Because if you rely strictly on the letter of the law of a standard, and it tells you recalibrate after 6 months, but in the process of training somebody new to your area, your equipment is damaged after 2 months, it will require recalibration before the period is due. So as much as I agree that there needs to be an overarching plan for how frequently your recalibration schedule is, I would prefer that we use a qualitative approach to how we schedule our recalibrations. If you notice drift in your instrument, recalibrate it, because the only thing that stops you from recalibrating your instruments might be resources. There's nowhere where it says you can over-calibrate. You cannot be overconfident in your results. If you're doing an 17025 calibrated results, at best you can get 97. Okay, from practice, there are people who maybe do better than 97%. Typically we do 95 and we're happy with 95. You can be stringent and even do 97% confidence. But let's not, because it's a question that always comes up at failure points. That's when we remember that we should have calibrated this instrument more frequently, rather than observing it continually, so that if you notice you had given it a schedule of 1 year, but due to how it's being handled, due to how it's being stored, or due to how maybe other factors that maybe you are not considered, its performance is not as you expect, you can always recalibrate. There's no, okay, let me say there's no reason why a competent auditor would question why you've calibrated your instrument multiple times if it's giving you continuous confidence in the results you're able to produce. So yes, your schedule may say every 6 months, but if I come to assess and you tell me it was due in October, but I recalibrated it in April because we have a training we want to do and we want to have confidence in the results we're getting, it's well within you because you're establishing confidence in your results. So to answer your question, for small medical devices, the typical guidance is every 6 months, but there's no reason why you can't calibrate at every measurement if you have the capacity. The same way for balances, for example. What we do when we zero them before we begin the measurement is technically a calibration. Every measurement is done after a calibration. So you can calibrate it as frequently as you need to establish confidence in your results.
And maybe to add on to that, a very classic example that we did when we were the construction of the Mombasa Road Namanga interchange. The company which was doing it was bringing their equipment for calibration every evening. When they are stopped working, they bring it, they calibrate, and they pick it very early in the morning. So you see, I think based on what Odak is saying, it depends on how you're using your equipment and what confidence are you trying to assure yourself. Yeah.
Yeah, before we close, Irene, do you want to add something?
No, I didn't get any question regarding the energy sector, so I would assume my presentation was quite clear, and everyone understood the importance of metrology in the energy sector.
I know that Lubonga wanted to ask a question to Kenjan, so maybe if there's an opportunity, he can, yeah.
Now, I just wanted to understand how the importance of calibration of your instruments, especially in the energy sector. How does it fit to your processes? Because you explained quite well how you do calibration, some of the tests that you do, how much data you gather, how you are able to do maintenance, preventive, and whatever. So I wanted to know how calibration fits into that, and if there is a place for metrological traceability of the measurements that you do when you're doing the preventive, maintenance, and also just how you check into your systems. Thank you.
Okay, thank you for your question. So calibration is quite important in the energy sector, especially for us where we've already set up a calibration center. So the accuracy of the data that we get from the instruments enables the controllers who control the equipment to make decision. Like when they are monitoring the machine and they see the temperature is going up on a generator, that informs them that we are probably overloading, so they'll be able to check the current, confirm whether they're overloading the generator, hence reduce the the load on the generator. They're able to make probably they could check readings concerning pressure, see what is happening, and from the readings they get, they're able to change the operations. If a machine is rated at maybe 80 megawatt, and you're told beyond this, below this megawatt, the vibration will be too much. So based on that, they'll be able to increase the load or decrease the load. So the accuracy of the equipment, the accuracy of the measurement is quite important for us to be able to make decision on how we run our machines, to make sure that they are safe, and to increase the lifespan on our equipment. Yeah, and that's why we normally do testing of the field instruments anytime the machine is out or we're suspecting the measurement is not correct. We also have our calibration center, which calibrates the equipment that tests the field equipment, and our equipment are traceable to cabs. So we ensure there is traceability in measurement for all our field instruments. Thank you.
And by the way, we give them traceability. They get traceability through CAPS.
And that brings us to an end of this important session. We really appreciate all the panelists and all the audience for your insightful questions and very informative answers that we received from our panelists. We really appreciate them, and we want to give them a round of applause for their participation. And I was asking Engineer Kabur earlier on that what is the a motivative music you guys have in Kenya? Say that we appreciate these panelists for their wonderful answers that they have been giving. So that's what we have.
No, I think our DJ is sleeping. Please give us a good.
So we really appreciate you, the panelists, Dr. Chow, Dr. Rotish, Irene, Mr. Odak, Warren, Denise, and all the panelists that have contributed to this insightful session. We really appreciate you. Thank you very much.
1545, see you that come through, see stress my come through, if you know what that means, you can number 2.
Welcome, Engineer Kabul, to close your program. Thank you very much.
Thank you, Isaac. Isaac Sunday from South Sudan Bureau of Standards. Yeah, I think we've had a really engaging day. First, I would like to thank all of you for being here up to, I think it's 5:15 now. Maybe give yourself a round of applause. That was not as loud as I expected, but I understand the energy levels not below. Santeni sana. I would also want to thank all our presenters today. We had our chief guest with his remarks, our MDs, our heads of delegation from different countries. And then we went ahead with our technical presentations. So you made the day happen. I would also like to thank my colleagues from South Sudan who are the session chairs for today. Asanteni sana. Bwana Mr. Atari and Mr. Sunday. Finally, before we end the day, I'd like to welcome one of you to come and close with a word of prayer. Then we can proceed for our tea just outside here. Any volunteer? Anyone who's courageous enough to say a prayer for us this evening? No, Isaac, are you volunteering yourself? No. Yes. Karibu, mpigie makofi.
Basi soma hiyo label 0023 tumakoda kikisha guarantee usipate umepima maji.
So good evening. I think I'm courageous. So let's close our eyes for the word of prayer. Our Heavenly Father, we come to you this evening. We thank you, Father, for your grace. We thank you, Father, for your blessings. We have had a very good session where we have been taught, where we have shared knowledge, and we thank God for that particular session. Father, as we plan to go back home, or where we are living, Father, we want to pray that God will be with us. Thank you, Father, even for the cup of tea that is ahead of us. We pray that you may bless that tea. We also pray for those, Father, who have nothing to take. Just like you have blessed us, also remember them and bless them, Father. We thank you for everything and glorify your name. And we pray this shortly, trusting your holy name. Amen.
Okay, that's it. I'll welcome you to just go outside and take your tea. For our Muslim brothers, please, and sisters, please wait here. Your iftar will be here in a moment. Then we can end the day. Asanteni sana.
You wanna go faster, faster.